Hi, I'm Val, and this is the fleet assignment lecture in the Airlines Management course taught at Linkoping University. So what is the purpose of fleet assignment? On the one hand, the airline has a set of flights that it has to fly, right? So you can think of it as a schedule. You have to go between certain origins and destinations at certain times, and that's the demand that you have to serve. On the other hand, you have certain types of aircraft. So these are your resources that you can use in order to serve the demand. And the goal of the fleet assignment is to assign different types of the aircraft to the different flights, which essentially tells you which aircraft type will fly which route. Know that you are not assigning concrete aircraft yet to every flight, to every link, but just deciding with which aircraft type you will cover one or another route. So here is the problem formulation in the nutshell. In the input, you have the schedule. Essentially, for every flight, you specify the origin and the destination, departure time, and maybe a few other things. And on the other hand, you have some specification of the available fleet. That is, you know how many aircraft of different types you have at your disposal. And in the output, you want to assign the aircraft types to the flights in the schedule. So here is the definition of the fleet assignment problem from the MIT course on airline management. And you will recognize the MIT slides by this blue background and white text. And they have in principle similar things in the input. You may see what they are. They are slightly different from what we had in the input, but still, in general, it's all the same. So you are given flight schedule. That's the same thing as we had, which flights you have to fly. Then this part, which says that each flight must be covered by exactly once by one fleet type. Well, I would say this is more of a constraint rather than the input. So the next part of the input is this number of aircraft by equipment type. This is exactly what we have. The specification of how many aircraft of different types you have. And I guess this is again more of a constraint, which says, well, you shouldn't overuse your fleet. You should only assign as many aircraft as you have available. There are a few other things that we don't have explicitly yet. These turn times, other restrictions, we will speak about them. Costs will come into the play, but not there yet. Anyway, you can see that what they have in their input is similar to what we have. And this is their output. So they, again, want to find, the important thing is that they also want to find the assignment of aircraft fleet types to the scheduled flights. Yes, they talk about minimization of the cost, or sometimes maximizing the profit. Yes, that's true. But that's more of the objective function. So the important part is, again, is this assignment, which we want to have in the output of the fleet assignment problem. And there are a few things. The maintenance requirements should be satisfied. The conservation of flow, we will speak about that. Yes, so not overusing the resources. All that is with us. So you may view the fleet assignment problem as the coloring of the links that you have to serve. So we were talking about the input as the schedule. We still have that. We may assume that any aircraft type has a certain color, like A310s are red, Boeing 747 the blue, and so on. And essentially, you want to color your flights with the different colors, meaning you want to assign different aircraft types to your flights. And here is from the slide from TNFL 01 lecture when it was taught by Tobias. I don't know if Christiane is still using these, but anyway, so this is an image that you might have seen. You have horizontal lines representing the different airports, and 1, 2, 3, and then every link, every arrow here represents a flight, and you want to color these links with different colors. So assign different types of fleets. So we will start with a really simple case, airline that has a single fleet type and hence single color. In fact, we will be starting with an even simpler case, super duper simple case, airline with just a single aircraft. Okay. And thinking of the problem that we have to color the flights by the different colors or different fleet types. If you only have a single aircraft, and hence, of course, also a single color, you may wonder if there is anything to solve, right? You have to assign the aircraft to your flights. You only have one aircraft. Well, then there is nothing else you, in principle, could do and just serve all the flights by your one and only aircraft. And despite the simplicity of the problem, there are still many questions that we may ask. So one question is the feasibility. You are given the schedule and you have one aircraft. Can you fly all the flights in a schedule with this aircraft? If you cannot, you may also ask a second question. Okay, you cannot fly all flights in your schedule with this single aircraft. You may want to maximize the number of flights flown. How to answer these questions? This is something we will be looking at. So first, let's look a bit closer into what we understand by schedule. We are given the schedule in the input. So we know for every flight number, for every flight that we have to take, we know its departure time, we know its arrival time at the destination airport, and of course we know the origin and the destination airports. So we will also assume that the turnaround time at every airport is the same, let's say 30 minutes in this example. So this is all we have to know as far as the schedule goes. The origin airport, the departure, the arrival airport, departure time, the arrival time, and the turnaround time. Okay. And starting from the schedule, we create the so-called time expanded network. It also has other names, time stage network, timeline network, but the important part is that it has an arc, a directed edge for every flight in your schedule. So again, this is one example that you might have had in TNFL 01. Here, every airport is represented by a horizontal line, like A, B, and C. And well, every flight goes from one airport to another, and the time goes from left to right. In the textbook, the airports are represented by vertical lines. The time goes down, and again, every flight is represented by an arrow going from the origin airport to the destination airport. In the MIT course, again, every airport is represented by a horizontal line, and well, you have the flight arcs, but you also have these what they call ground arcs, which here's an example of the ground arc, like this one, and this one, it goes from the airport kind of to itself. Anyway, again, here are the airports represented by horizontal arcs, and the time goes from left to right. You may, in principle, represent things even in X, Y, T space. So the airports would have certain locations, and you could have a vertical line at every airport representing that airport, and again, the flights would go between the lines representing the going from one airport to another. So in this course, we will of course use one line per airport, and the lines will be vertical, and the time will go down. So every line here is an airport. So it's airport A, B, C, and so on, and the time goes down. Okay, that's just a convention, as good as any other, but we have to stick to one convention. Now we will look more closely at the arcs, or these arrows, the directed edges that represent the flights. So it is quite natural that any arc representing a flight is directed from its origin airport to its destination airport. And let's see now what are the origin and the end of every arrow. So the tail of every arrow is called the departure node, and well, it starts at the origin airport, as we said, and the time when it starts is the time of the departure. Everything is quite natural. Why would it be otherwise? Now, when it comes to the end point of the arrow, of course, it goes to the destination airport and thus represents kind of the arrival node. But the time to which it goes is not the arrival time. It's actually the arrival time plus the turnaround time. Okay, so what it represents is that the end of this arrow represents the time when the aircraft is ready to depart. So maybe it has arrived over here, but then it still has to spend some time on the ground before it is ready to take off. So here is the illustration. It might have arrived early. It needs to spend some time to do the turnaround, and then it's ready to depart at the time to which the end of the arrow points. Sometimes this is called the ready node, and sometimes such a timeline network is called the ready time network. So this is the convention that we will be using. Every arrow representing the flight goes from, of course, from the origin airport to the destination airport. It starts at the departure time, and it ends at the time when the aircraft is ready for its next departure. Okay, what other arcs, what other arrows do we have in the timeline network? We have the so-called remaining overnight arcs. So we will use the shorthand RON. RON will represent remaining overnight. So such a RON arc, like this one illustrated here, it represents the aircraft staying overnight, remaining overnight at this airport. So we will have one RON arc per airport. At what time we are counting the aircraft? Well, we may assume, I don't know, that we have a mid-sized airline that doesn't have any intercontinental flights. They don't fly red-eye back and forth. They, at let's say at 3 a.m., all the aircraft of this airline are on the ground. since we are still talking about an airline with a single aircraft, we assume that every night the aircraft stays at a certain airport. Yeah, at 3 a.m., if it is in this airport, then the aircraft kind of follows this Ron arc, if you think of the time. Sometimes you may see in various models, in fact, in almost all models except for the model in this course, you may see ground arcs that as already mentioned and showed on the slide from the MIT lecture. They represent the aircraft staying on the ground at the airport at different times. In this course, we will not going to have ground arcs. I'm trying to present kind of what I call the minimal non-trivial model. It's the model which is rich enough to solve the fleet assignment problem, but which doesn't have anything extra, anything which is not needed. And turns out that we can get away without using ground arcs, so I'm not introducing them. But we will see how they are introduced in the fleet assignment model in the MIT course, and you also have ground arcs in the book. In addition to ground arcs, there could be many other kinds of arcs. So here again, the timeline network from the MIT course, and you see that it does have some of these wraparound arcs. So these are the remaining overnight arcs. So again, the time goes from left to right for them, and then yes, here is something that represents aircraft staying overnight at an airport. Here again, the ground arcs in the MIT course. We don't have them. Here are many other arcs and nodes that you might see in the textbook. So yes, there are certain flight interconnection arcs. Yes, there are of course remaining overnight arcs. Yeah, so there is a lot which you can see in other courses, but which we do not use. Yeah, like these interconnection nodes for conservation, whatever they are, you may check the book what they represent. Okay, so this is our timeline network, or time expanded network, or anytime network, whatever the name of it. The important thing is that it has a line for every airport. It has these arrows representing different flights, and it has these remaining overnight arcs representing the aircraft staying overnight. We will assume that we always have different times for any operations. So we do not have two departures scheduled at the same time even in different airports for our airline. So if that's the case, you can slightly shift the departure time, for instance, shorten the turnaround time, and yeah, this way break the ties and safely assume that any operation happens at a unique time. Operation, I mean departure or arrival or being ready. Okay, that's just a technical assumption which will help us. So here's the schedule. Again, we're coming back to the schedule with 5 flights, and here below you see the network for this schedule. We have 1 to 3 airports, so 1, 2, 3 vertical lines, and 5 arrows for the flights, and 3 remaining overnight arcs, 1 per airport. If you want to see whether your schedule is implementable, what you may do is to follow the so-called earliest departure first or greedy strategy. So you have your aircraft and you have your schedule, and you're trying to understand whether you can implement the schedule with this aircraft. Well, here is your departure with the earliest time, right? You have to fly this flight. So you say, okay, I will fly that. Then you need to fly this one, okay. Then the earliest departure after that is this one, so you need to fly this one. Then you have to fly this one, and so on. And this way you can check whether your schedule is implementable, whether the single aircraft is enough to fly all the flights that you have to fly. A simple strategy. However, if you want to solve some more complicated problems, for instance, if you cannot fly all the flights in the schedule, and you have to decide how many flights you can fly with a single aircraft, or if you go to the more interesting questions when you have more than a single type of aircraft, or just more than one aircraft, even if all your aircraft of a single type, you really have to do something more complicated than just looking at the timeline network. And specifically, you would have to use the mathematical program for the fleet assignment. So this is kind of the golden standard of solving the fleet assignment problem. It's been used everywhere. And this is what we will be studying for the rest of the course, the mathematical program for the fleet assignment. Again, it's been used not only in our course, almost the same mathematical program is being used at MIT. We will also study their mathematical program. The mathematical program in the book is also very close to what we and MIT has. In the industry, I might have mentioned it before, but in general, you know that within the FTL program, we often have guest lectures coming from various places in the industry. And a couple of years back, we had guest lectures in TNFL 07. They came from Jeppesen. Jeppesen is the, well, Boeing subsidiary. It's the company that produces software used by various airlines, in particular to solve their fleet assignment problem. And the lecture given by Jeppesen was very interesting, but also a bit frustrating. So the fact was that they didn't give us any new information of, you know, saying that, well, in the industry we do things so and so. No, turns out that they use exactly the same mathematical program, well extended, of course, and applied to real, to the real cases. But still, this was the way to go. So we kind of didn't learn anything new from them. But it was also good to know that we are on the right track and learning the right tools. Okay, mathematical programming. Just to remind you a couple of slides of what it is about. In general, the programming framework creates a mathematical program for your problem. In the mathematical program, you have variables. Usually they represent the decisions that you make, and they are called the decision variables. Then the requirements that you have in your real problem are translated into the constraints of the program. And last but not least, you often have the objective function, both in your problem and in your program. And this is something you're trying to minimize or maximize. So in particular, in our case, we will be looking at the schedule or at the timeline network, and we will be creating the mathematical program for fleet assignment. So the two important things about the mathematical programming framework is that the instances of the problem should be in one-to-one correspondence with the mathematical programs, in the sense that if you have a solvable instance, if there exists a solution to your problem, then the mathematical program should be feasible, meaning that there should exist a solution to it, or in more details, meaning that you may assign values to the variables in the program that satisfy all the constraints. Okay. And on the other hand, if your problem instance is not solvable, if there exists no solution in it, then your program should be infeasible. No matter what values you assign to the variables, at least one constraint will be violated. So that's very important thing in the mathematical programming framework. And also, as mentioned, different solutions to the problem may have different costs, and these should be reflected in the objective function value in your mathematical program. So any solution having certain costs should correspond to the objective value having the same cost. In particular, meaning that the optimal solution to your problem will be represented by the optimal solution to the mathematical program. Okay, so that was a very general description of the framework. And now we will get to the crux of the fleet assignment, particular fleet assignment mathematical program, and look at the different variables that we assign to the links and to different constraints. So now is kind of the most important part of the lecture, and if there's ever a time to take a break, maybe now is the right time. Okay, so first of all, we will have one variable per link in our schedule. So just to remind you, any link has the departure airport or origin airport, time of departure, the destination airport, and the time when the aircraft is ready, to which the arc is pointing. And sometimes we will be sloppy and say that, well, this time is the time when the aircraft arrives, even though we will mean that the aircraft is ready at this time, that it arrived maybe a bit earlier, and some time has passed for the aircraft to finish its turnaround process. So we will be sloppy in using this both for ready time and for the time of arrival. So we'll say the aircraft departs at this time, arrives at this time. It will be just more convenient. So every link is characterized by these four things: the origin airport, destination airport, departure time, and arrival time, or ready time. And just as we were describing objects by their properties, we will say that any link is the collection of these four things, or four numbers. Well, two of them are numbers: the departure time and the arrival time, and two airport names. So any link L consists of four things: origin airport for this link, the destination airport for this link, the departure time, and the arrival time for this link, right? So the variable that is assigned to link L will be the variable XL, and it will represent whether this link is actually flown by your aircraft or not. So if link gets the variable equal to 1, then you fly this link, and if the link gets the variable assignment of 0, then you don't fly this link. Again, pretty natural. Similarly, we will have the variables on the remaining overnight arcs. At every remaining overnight arc, we will have a variable that represents the number of aircraft that stay overnight at this airport. And we will index them by S, well, assuming that S is the station We could have indexed them by A, saying that A is the airport, but then A could also stand for arrival. Anyway, the notation is kind of the best I could come up with. If you have a better suggestion for a notation, you may use that. But we will use S to represent an airport and XS to represent the number of aircraft staying overnight at this airport. So those are the variables. Now the constraints. So imagine you sit at this airport S and you're watching flights coming in and out the airport. So you probably want the total number of aircraft that arrive equal to the total number of aircraft that leave the airport. Because otherwise you would be either accumulating aircraft at this airport from day to day, or you would have to produce the aircraft at the airport, right? If you have more aircraft arriving than leaving, then, well, you would have to do something with those extra aircraft that have arrived. On the other hand, if more aircraft leave the airport than arrive to the airport, well, you would have to compensate somehow. You would have to produce the aircraft in the airport. So what you want to have is an assignment of variables to the links such that the total number of aircraft that departed is equal to the total number of aircraft that arrived. Or if you just look at these arrows that originate and end at the airport, the departing aircraft are the aircraft departing from the airport, and also the aircraft, well, kind of departing to stay overnight. And similarly, the arriving aircraft, well, one aircraft kind of arrives from staying overnight, and there are also a few other aircraft that arrive during the day. So you want to have this constraint. The question is, how do we write this constraint using our variables and using the notation that we have introduced? So how do we write the total number of aircraft that departed from the airport? So recall the convention that any link is characterized by four things: the origin and departure, and destination airport, departure and arrival time. And we want to count the aircraft that depart from airport S, right? So we want to count, to somehow write the expression for the total number of aircraft on these links. This, and this. Now, what is the common part of these links? How do we single out them from all the links at this airport and maybe all the links in our full timeline network? What is so special about these links, the links that originate at airport S? Well, all of them have this thing in common. All of them have origin at S. Or in other words, origin of L is equal to S for any link L originating from airport S, by definition, right? So if you want to sum up the number of aircraft that departed from the airport S during the day, you have to sum up the values of the variable XL on all these links that have S as their origin. Similarly, if you want to count the aircraft that are arriving to the airport S over the day, you would have to single out these links, the links that have the airport S as the destination, and again sum up the variables on those links. Okay, So here is the expression for the number of aircraft that depart from the airport during the day. You summing up these variables, XLs, over all links that have S as their origin, right? This expression represents the number of aircraft departed from the airport during the day. You summing up the variables on all these links, and these are the links that have S as the origin. And you want that to be equal to the total number of aircraft that arrived to this airport during the day. And well, here is the expression for that. This one. It looks at all these aircraft that have S as the destination, all these links that have S as the destination. And you summing up XLs over those links. Okay. So this whole thing, or each of these, is probably the steepest place in the learning curve for this course. If you understand how this works, then you understand everything else easily. The rest is kind of building on top of that. The extension to the case of the airline with multiple aircraft of a single type, and then extension to the case of, the most general case of the airline with multiple fleet types. All of these are easy steps if you understand this. So I will repeat this again. You are summing up XLs, the assignment of variables to these links. To which links? To all these links that have S as their origin. And this represents the total number of aircraft that departed from airport S over the day. Similarly, this represents the total number of aircraft that arrived at S during the day. So we have one constraint like this per airport. Well, there are more constraints that we need to take into account. Even if you have, the same amount of the same number of aircraft that departed and arrived to the airport over the day, still it could be that all the aircraft are departing in the morning and then arriving in the night. And if you didn't have enough aircraft staying overnight, then you may not have enough aircraft to serve all the morning departures. So in particular, in this figure, well, you may say that, okay, maybe one aircraft stayed overnight and then it departed. And then the aircraft arrived again and then it departed. But then you have a departure like this. And the question is, well, you don't have aircraft to serve it because by this time, you haven't had enough aircraft that arrived to serve this departure. So what it tells us is that we need a constraint that the number of aircraft that departed by any time during the day, so you look at any time during the day, the number of aircraft that have departed by this time should not exceed the number of aircraft that are ready by this time. And the ready are the ones that have arrived plus the ones that also stayed overnight. So we need to add a constraint like this, that at any time we don't have more departures than arrivals. One problem is that, well, there are too many times. In principle, there is an infinite number of times. We don't want to add a constraint like that for every single time. But we may look at the question, when could these numbers change? When could we have a change in the number of aircraft that departed by time t, or in the number of aircraft that are ready by time t, have have arrived by time t. And come to think of it, it could be only during arrivals or departures that any of these numbers change, right? In here, in between the arrival and the departure, neither this number nor this number changes. So we only need to ensure that these constraints hold at every arrival and every departure time. And that already gives us a final set of times when we would have to write these constraints. But looking a bit further, we can say, well, you know, if you had this constraint satisfied and an aircraft has arrived, then the constraint is kind of satisfied even more, even better. You have even more aircraft. So the only time when this constraint can be violated is during a departure, right? So if this constraint was satisfied and an aircraft arrived, and then well, this constraint is still satisfied. It is only during a departure that this constraint may be violated. So what we really want to do is to write this constraint for every departure node. Now, how do we write this constraint that at any departure node, the number of aircraft departed by that time does not exceed the number of aircraft already by that time? Again, we look at our notation for the links. Recall that every link is represented by 4 things: origin, destination, airport, departure, and ready time. And we will try to use this representation to write an expression for this, for the number of aircraft that have departed by the time t. Okay, so here is the departure time, here is the departure time. What is the total number of aircraft that have departed by a certain time t? How do we write that? Well, we have to sum up the variables on these links that represent the aircraft that have departed by a certain time t. How do we do that? Well, as before, we are looking only at the aircraft that have S as their origin, right? So we are only focusing on this airport S, and in particular, we're looking at the flights that have departed from this airport S. So we're only looking at the links such that origin of the link is equal to the airport S. But in addition, we don't want to sum up the variables on all the links departing from this airport. We only want to look at the links whose departure time is smaller than t. So if this is t, then we want to look at this one and then this one, up to and including t. We don't want to sum the variable on this link if this is our time t. And therefore, we're adding this extra condition that we're summing over links that have S as the origin and have the departure time earlier or equal to t. So altogether, this represents the number of aircraft that have departed from S by the time t. Okay. And our constraint that we want to write says that this value, the number of aircraft that departed by the time t, should not exceed the number of aircraft that are ready for the departure by time t. And here is how it's written. More or less same thing. So we are looking at the aircraft that have arrived to the airport S. That is the aircraft that have S as their destination. But in addition, we don't want to look at all the aircraft that arrived at S. We only want to look at aircraft that are ready to depart by the time t. So this represents the number of aircraft that have arrived at airport S by the time t. And we also add the aircraft that maybe stayed overnight at S, because of course those aircraft that stayed overnight, they are ready to depart at any time t. So this is how we write the second constraint, the constraint per departure node. Okay, and last but not least, we have to ensure that we do not use more aircraft than we have. In particular, if you look at this example, at this network, and you know, some assignment of variables to all the links, well, we can say that per airport, if you only look at a single airport, things look good. You know, an aircraft stays overnight, flies out, flies in, stays overnight. Similarly, at this airport, an aircraft stays overnight, flies out, flies in. But altogether, across the two airports, we have used two aircraft. And maybe we only have a single aircraft. We're still in this case of the airline with a single aircraft. So we have to introduce some kind of inter-airport constraints, the sizing constraints, the constraints that would count the number of aircraft that we have used. Well, one good time to count the total number of planes used is, you know, 3 a.m. when they all sit at their airports. So we're just saying that over all airports, the total number of aircraft that stay overnight at the airports should not exceed 1, because we only have a single aircraft at our disposal. Okay, so that's the last constraint. And here is the fleet assignment mathematical program. All constraints at once. There is one constraint which we can call the flow conservation constraint. The aircraft out should be equal to the aircraft in. Then there are these constraints, one per departure node, the non-negativity constraints, saying that you should always have enough arriving aircraft before any departure. And last but not least, the sizing constraint, the kind of inter-airport constraint, saying that altogether you should not use more aircraft than you have. And in this case, do not use more than one aircraft. And then at the bottom, there are also a couple of technical assumptions. Yes, we're assuming that all the variables are integers, larger than 0 for the remaining overnight arcs, and zeros and ones for the for the variables on the links. Okay, so these are all the constraints and all the variables, and here's the fleet assignment mathematical program for you for the case of the airline with a single aircraft, of course, of a single fleet type. And we will look at an example of this in the next lecture, and then, of course, extend it to the cases of the airline with multiple aircraft of a single type, and then for the airlines with aircraft of more than one fleet type.